When I began work as an undergraduate research assistant in the Susan Golden Meadow Laboratory, I learned many things. I learned how to collect data. I learned how to build an Excel sheet. I got very good at carrying a very large video camera as well as a very large chalkboard as I schlepped around Hyde Park in search of children from whom we could collect data. But what I really learned was the joy in asking simple questions and coming up with elegant ways for answering those questions. Susan Golden Meadow has had an incredible career, and one thing that she does exceptionally well is support her students in asking interesting questions, thinking hard about those questions, and coming up with answers to those questions. Today, I'd like to tell you about a study that addresses the very same question that we were answering many years ago, and that is, how does gesture work? Today, I'm going to tell you about a study that asks how gesture might support math learning. We know that gesture, in fact, is useful for math learning. Children who learn from instruction that includes hand gestures learn more than children who learn from instruction that doesn't include hand gestures. The question for today is how? What is gesture contributing to children's developing mathematical understanding? There are a variety of hypotheses for what gesture might be doing, some of which we can test or will test in the current study. So one possibility is that gesture might help disambiguate speech, clarifying the meaning that an instructor is conveying as she refers to various mathematical entities. A second possibility is that gesture might help children create knowledge, supporting creation of procedural knowledge that allows children to successfully execute the steps required to solve mathematical problems, or supporting the creation of conceptual knowledge that provides the overarching framework and the principles under which those procedures operate. Gesture might also support various cognitive processes that are involved in learning. And one part of conceptual change that seems particularly important in math learning is resisting interference from prior knowledge. So developing mathematical knowledge often requires overcoming the limits or weaknesses of our previous knowledge as we learn increasingly abstract and differentiated mathematical concepts. So in the domain of mathematical equivalence, children often arrive at our instruction with an incorrect understanding of the meaning of the equal sign. If we ask them, they say things like, it means put your answer down, it means math. When you write a math problem, it has an equal sign. So they understand that the equal sign is an indication to do something, an operational understanding. But in order to acquire a relational understanding of equivalence, which is what gesture has been shown to support, children need to overcome this prior knowledge. And so the question that we asked in this study is whether gesture was especially good at helping children overcome their prior knowledge. The design of the study was simple. It was a 2-day study. On day one, children completed a pretest. We'll use this to measure their prior knowledge. They then completed instruction where they acquired some knowledge. They then participated in an interference condition, which was designed to either reactivate their prior knowledge or not. Then a post-test. Did they recall what they learned from instruction? And a generalization test. Could they generalize that understanding to new problems? On day 2, they completed a second post-test that was designed to measure consolidation, some true-false problems that measured their conceptual knowledge, a task where they were asked to define the equal sign. This was a written task, and children did very poorly at this task, so we dropped this from our analysis. And then finally, a task where we asked them to circle the side of an equation, which was designed to assess their referential understanding. Right. So on the pretest, we gave children 2 problems. And what we found is that children children had 2 different sorts of prior knowledge that they brought to our learning environments. Some children solved the 2 pretest problems by adding up all the numbers, and other children solved the 2 pretest problems by adding up the numbers until they reached the answer blank. We had 113 kids who added all the numbers and 124 who added up to the blank. After the pretest, children participated in instruction, and I'll show you a little excerpt from the instruction. During the instruction, the instructor either gestured or not, and other aspects of the instruction, including eye gaze, body position, and prosody, were carefully controlled. So I'll let you see what that looks like here.
Remember, the equal sign means that the total amount on the left side must be the same as the right side. This will help us figure out what goes inside the blank. Let's figure out how to do this. 6 plus 2 equals 8. 8 plus 9 equals 17. And what number plus 9 also equals 17? 9 plus 8 equals 17.
All right. So important to note about the instruction, we explained a completed problem using a highly informative explanation that was based on principles of mathematics instructions. The gestures were designed to delineate the two sides of the equation. We consistently use the left and the right hands to refer to the two different sides, and we use the same hand shape to indicate that those sides were different but the same. And this instruction was delivered at the classroom level. Children watched videos in their classroom. After instruction, children completed some problem-solving booklets that included either the interference or control condition. In the interference condition, children solved some simple addition problems that were designed to reactivate that prior knowledge of either adding all the numbers or adding up to the answer blank. Meanwhile, in the control condition, children solved some problems, but the numbers were oriented vertically. And so there wasn't an equal sign. There wasn't actually an answer blank. And so the idea was that these problems wouldn't activate the knowledge that they had used to solve the pretest problems. So we had 404 second and third graders. They participated in their classrooms. We included school and grade as control variables in our analysis since both had strong associations with performance. So first, we can ask the question, does gesture help learning? What we see is yes, there are consistent effects of gesture on students' performance, replicating previous work. So children who learned with gesture did better on day one during the instruction, on day one on the equivalence post-test problems that they solved immediately after instruction, on day one, the generalization problems that they solved next, and then on day two, on the equivalence problems that they solved again. We didn't see differences on the day two true-false problems or the day two sides problems. And so this suggests that what gesture helped children do was correctly solve problems. It didn't help them with their conceptual knowledge, and it didn't help them with referential understanding. We didn't see benefits for the gesture group in the problems designed to assess those two potential mechanisms by which gesture might affect learning. So if we think a little bit more deeply about memory, we can ask what aspects of memory gesture might be supporting. And in fact, what we find is that if we control for performance during instruction, we no longer see differences on the remaining problem-solving tasks. So what gesture seems to be doing is supporting children during instruction. So in this case, gesture seems to be helping children overcome their prior knowledge, which represents a barrier to accessing the information that's presented during instruction. So we can ask then, how does gesture interact with interference? Unfortunately, what we saw, so on this graph, we have the no gesture kids in the left and the gesture kids in the right. And then we have the control group with circles and the interference group with triangles. The important thing to notice here is that there were actually no differences across our interference conditions. So our manipulation, which was designed to interfere with children's learning, was unsuccessful in disrupting that learning. And it didn't matter whether children had learned with gesture or without, regardless of what sort of problems they performed after instruction, we saw the same pattern of performance. So next we can ask, which children benefit from gesture? Does children's prior knowledge influence the learning that they get, the benefit that they get from gesture? So next we can ask, which children benefit from gesture? Does children's prior knowledge influence the benefit that children get from receiving gesture during instruction? And so we divided our kids up into two groups on the basis of their pretest performance. On the left here, you have the add to blank kids, and on the right here, you have the add all kids. And then we have the solid lines representing the no gesture condition and the hashed lines representing the gesture condition. And what you can see is that for the children who arrive at instruction by adding up all the numbers to the blank, those children show no differences. They do no better if they receive gesture than if they don't receive gesture. In contrast, for those children who arrive at instructions using an add to all problem-solving strategy, Gesture makes a difference. Those children show benefits of gesture, both during instruction, and then we saw significant improvements in performance on day 2 equivalence problems, as well as day 2 true-false problems. So what does this mean? What this means is that gesture seems to help some children more than others. Specifically, gesture seems to help children differentially depending on their prior knowledge. So we can put all these bars on the same graph to get a better sense of how performance across the two different groups of children, as well as the two different instructional groups, compare. And that's what we have on the next slide. And what you can see here is that for children who arrive at instruction with add-all knowledge, clearly those children benefit from gesture. They do better than all the other children on their problem-solving performance. We also see that the add to blank children show a slightly different profile. Those children seem to show a benefit or better than expected performance compared to the add-all children on the day 2 true-false problems. So it's possible that add to blank children have advanced conceptual knowledge that isn't supporting problem solving. It's also possible that this is due to characteristics of the problems used across the different tests. So children who are using an add to blank strategy are attending to the blank and using the blank to guide their problem solving. Of course, the blank isn't going to guide them in the correct direction, and that's going to cause them problems on all the problem-solving tasks, as well as on the sides tasks, because all of these problems have blanks. But the day 2 true-false problems don't have blanks. They represent completed problems that children have to judge as either right or wrong. Now, interestingly, our instructions also included completed problems. That is to say, they didn't include explicitly the feature that was driving problem solving for the add to blank kids. And so perhaps it's not surprising that gesture didn't help those children, right? If the instructions don't target your own prior knowledge, which is likely to be a source of proactive interference and disrupt your learning, then you may be less likely to benefit from those instructions and less likely to benefit from gestures that can support you in overcoming that prior incorrect knowledge. Of course, we'll have to do additional work with different instructions in order to see whether this account is true. But it's certainly possible that different instructions would similarly show differential effects on children, as we've seen here. So what did we find? Well, first of all, we found clear evidence that gesture benefits learning, even when it's presented in conjunction with a rich spoken explanation and when presented at the classroom level with video. Gesture has effects on acquisition that support subsequent recall, generalization, and consolidation. And this is consistent with the idea that gesture helps support children in overcoming proactive interference. If we want to know how gesture works, the story is going to be a little bit more complicated. The benefit of gesture depends on children's prior knowledge. So what did we find? What did we find? We found two clear effects. First, gesture benefits learning, and this is true even when it's presented in conjunction with a rich spoken explanation and when presented at the classroom level. We saw that gesture had effects on acquisition of new problem-solving knowledge, and this new knowledge can support recall, generalization, and consolidation. We also found that the benefits of gesture depend on children's prior knowledge, and this suggests a mechanism by which gesture might be supporting learning. It might be helping children overcome proactive interference. Of course, additional work will be necessary to confirm this account. But we want to think a little bit more broadly. We can clearly state that gesture is not a panacea. Children who learn with gesture do not always perform better than children who learn without gesture. Instead, we can conclude that children's prior knowledge and characteristics of instruction interact to support learning. How gesture works depends on who you are and what you need to know. I'd like to finish up by saying thank you to Susan Golden Meadow. Thank you for being an incredible mentor and friend. Thank you for your unwavering support, for your brilliance, for teaching me what it means to be a mensch. I'll be forever grateful. With that, I'd like to thank you for listening and open it up for questions.